Okay, the first question for the week here comes from 4.58, and it's 2, 2, 3, 3 tetra methyl butane. And I wanted to talk about this for a little bit because it's more common than you may realize. It says sketch an energy diagram, determine the energy difference between the staggered and eclipsed conformations. Well, first you need to be kind of familiar with what the molecule is going to look like. So you got a butane. This is one way to draw it. And off the second one, let's call this the second one, you got a methyl and another methyl and another methyl off the 3 and another methyl off the 3. Whoops. And if you count this up, this is 1, 2, 3, 4, 5, 6, 7, 8 carbons. This is actually what they use as the reference chemical for the butane in gasoline. And it's kind of a round shape, a ball shape, sort of. We've discussed this before. And if you're going to burn these carbon and hydrogen atoms in this molecule with oxygen, it's going to burn slower than other forms, which makes gasoline burn smoother. So your octane rating on a gasoline is a comparison of how that gasoline burns compared to a 100% solution. Well, 100% would be a solution in that case. Sample of this butane isomer. It's more complicated than what I just described if you get into petrochemicals, but basically that's what's going on. Now, what we want to do is see what's going down as you look between these two carbon. I don't have one of these like this, but the central carbon is down this way. So you got this one, and this one is this one, and this one, and the other methanes are hanging around there. And you did pretty good with this. So the back, if you're looking at it down that way, the back would look like so. And the top one, the front one, would look like so. And together, they would look like this. And so basically, everything's pretty symmetrical. As this rotates around 60 degrees, you would have eclipsing interference, and then staggered, and then eclipsed. Whoops, eclipsed here, and then staggered, and then eclipsed, and then staggered, and you probably noticed in one of my previous videos I said eclipsed a couple of times where I meant to say staggered. I imagine you figured that out. But if we were going to draw a graph of that, at least your graph is symmetrical because they're either eclipsed or they're staggered and everything's methyl groups. So you would have, if you go all the way back to 4-6 on page 161, there was another table we looked at where we were looking at the strain and the repulsion between groups and atoms in rings, cyclohexane rings, but here we're just looking at how they line up like so. And we've got methyl and methyl, so they either are, when they are eclipsed, we've got 11 apiece. When they are staggered, they have a steric hindrance of 3.8 apiece. And since there's 3 sides to this looking down from above, then it's 3.8 times 3 versus when they're eclipsed, they're 11 times 3. So the peaks, you're going to have something like this. Peak, valley, peak, valley, peak, valley. That's very bad. Peak, valley, but the peaks are 33 kilojoules per mole. And the bottoms are, I think, 11.4 kilojoules per mole. Maybe I didn't do this right. It should have been more like this. Okay, where the bottoms are 11.4 kilojoules per mole. Something like that. Okay, 4.59 says, rank the following conformations in order of increasing energy. And without looking the numbers up on that, so see, let me know if you got something different. But I came up with the lowest would be the one that had the bromine. Oops, those are supposed to be together. On opposite ends of the molecule. Something like this. If these green ones were bromine, it would be like so. Like that. And then the next one I had was this one. Where I had them staggered, looking down this way. Again, these are chlorine in the model kit, but I'm not going to change them here. They'll work for calling them bromine. And then the next one I had, with more energy, was this one. Whoops, this should be BR. What should be, well, pretty much like that. And then the highest one would be with the bromines lined up like so. Something like this, like that. I didn't triple check to make sure that was right, but that I just kind of did that one. It seems right to me. Okay, let's see if we can make another page here at least. 460, compare the two conformations of 2,3-dimethylbutane. Determine the total energy cost associated with all torsional and steric strain. I've already got this one drawn out, so let me just use this one. If you have this one, there's an 11.4. You go back to that table again on page 161. Right here. There's a, if their methyl groups are eclipsed, you have a torsional and steric hindrance of 11. If they are staggered, it's 3.8. And the way I have that, let's see here. Also, I got to do this one. The torsional strain between H and CH3 is 6. Between H and H, it's 4. So, I'm not sure I did this one right, but I guess between these two, I have an 11, an 11, and an 11 point. I don't know how I got 11. No, I guess I have a 3.8 and a 3.8 and a 3.8. Gives you an 11.4. What I don't have is one for this. So I've got, oh, for eclipsed, you don't have anything for the hydrogen. Eclipsed with methyl, I don't have anything. Okay, so this is 11.4. Let's trust my first instincts, I guess. When they are staggered, or when they are eclipsed, these are all staggered. That's what I should have been saying. When they're eclipsed, these two are 11. these two are 6, and these two are 6, and that totals to 23. So I had that right the first time. Again. So that's total energy cost. So this one's got more energy in it. This one's more stable. I didn't double check this, but if we go with 4.61, I drew this one first, and when I got that done, I only had one that was axial. The rest were equatorial, out there not bothering anybody. So I didn't bother to draw the other one because I knew that wasn't going to be the answer. So this is going to be the more stable one with one axial hydroxide. See what else I have here. I will let you check the answers on 462. You probably didn't have any trouble with this one. But for A, if I'm at so you have to go through these and figure out which ones are which position. So at C2 position, if it's up or it's axial, what do you have? You have to identify it's equatorial, axial. And then I double check these, but for A, I have equatorial. B, I had equatorial. C, I had axial. D, I had equatorial. E, equatorial, and F, axial. So if you have a different answer on one of those, let me know. And if you do draw out propylene the way they have it there, and you put the hydrogens in, this is propene. You don't have to worry about if it's, this is always going to be the one end. So you got ethene, propene, butene. Once you get to butene, you got to worry about where that goes. You don't have to call this one propene, because then if you flip it around, then the other end is the one propene for the double bond. Okay, and while I'm on this page, I'll do the last one. I'm not sure I can explain this well, but let me draw it again. This butane, we've tried to do this before. It's not going to be flat. It's going to have strain on it. So it's a cyclobutane. I don't know what I just said there. So it's going to be more like this. Okay, so if I draw the hydrogens in there, maybe this one they'll be down or something. I had them drawn up there just to, actually they'd be kind of out. One would be kind of up, and can't really draw it. It'd be kind of that way off the other side. You could, I suppose, do something like this. I think they call that a Hayworth projection. And then you're going to have a chlorine up here and a hydrogen down here, because this one's up and then this one's down. Okay, so if you did that, then you'd have a dipole on this chlorine kind of this way, and a dipole on this chlorine kind of this way. And those don't cancel. They have kind of if you add that vector to this one, and I know this course we didn't do vector addition, but in physics we do. If you did something like that, you'd end up with a net vector addition, like so. That's how you add vectors. So you kind of have, not sure exactly where this would go, but two halves to a molecule where one side's kind of positive and the other side's kind of negative. You guys are pretty good about that. I think that was chapter 6 maybe from your last year's chemistry course. So you had a handle on kind of how you ended up with a molecular dipole. But that's kind of what would happen there.